All right, so let's try to finish off the chapter. So we'll talk about temperature dependence, a little bit about reaction mechanisms, and then lastly we'll discuss catalysts a little bit. And I'm going to kind of skip over some of this just because there's a lot of detail here and it can be overwhelming. So I'm going to kind of simplify this down a little bit to what I really think you need to know. So firstly, we know that generally speaking, as temperature increases, the rate of reaction also increases. But so far we've been discussing rate laws, and at no point have we discussed temperature, aside from saying, okay, this reaction occurs at this temperature. Well, so in other words, there's no temperature term in any of the rate laws. Well, there is actually, because it's built into our constant. Okay, so our constant is actually temperature dependent. So that means anytime you mention a rate constant, you have to mention at what temperature. So is it at room temperature? Is it at the boiling point of the solvent? Where is this actually at? Okay, if we take a look at this, so here we have a plot of our K value versus temperature. And we just have a simple reaction. So we have methyl isonitrile becoming acetonitrile. Okay, so we're going through a rearrangement essentially. And what we see is that as we increase temperature, we actually increase our K value pretty much exponentially. Okay, and so what is that telling us? It's telling us that within our K value, we've already accounted for temperature. So remember, our rate for this reaction would just be rate is equal to K times the concentration of our reactants. So our K value is already building in that temperature term. Okay, this next part is called the collision model. And so sort of at the beginning, we talked about concentration a little bit. And I mentioned one thing, that if we're able to have more collisions with the molecules, obviously that's going to lead to a faster reaction. Well, what's another way to increase the collisions aside from increasing the temperature? Aside from increasing the concentration. Well, another way is to actually increase the temperature. Okay, so what do I mean by collisions? Well, in order for two molecules to interact, in order for a reaction to occur, we have to have a collision. So if two molecules can't interact, then there's no reaction. Okay, so here we have chlorine reacting with a nitrogen-based compound to give us NO and then chlorine gas. So what's happening here is chlorine is coming in, bonding with the chlorine attached to the molecule, forming chlorine gas, and leaving behind a lone pair of electrons. Well, actually it's leaving behind just one electron. Okay, that part's not so important, but what is important is the actual collision model. Okay, so what's happening here is this chlorine has to actually come in and meet this chlorine. Okay, so before the collision, they're both just either swimming through solution or swimming through space as a gas. Okay, and then once they meet each other, boom, they collide. Okay, so now a reaction happens, and the result of that reaction is that we break this bond and we form a new bond between chlorine. So as the reaction gets carried out, the molecules then move away from each other. Okay, so it's like they flew towards each other, smashed into each other, and then they kept on moving. Okay, and so the more collisions you have, the faster that reaction will be. And this bottom one is showing you, so the top, that was an effective collision. The bottom is an ineffective collision. So if instead that chlorine atom smacks into the oxygen side, well, then nothing happens. They just bounce off of each other. So what we want is to have more effective collisions in order to increase our reaction rate, which means what? We want to have just more collisions overall. Sorry, I'm sniffing. I just cut some onions. So we need to have more collisions in order to have more effective collisions. So raising the temperature, we put more kinetic energy into the molecules. They're moving faster, therefore they have more collisions. Okay, so this is also built into our K. So the collision factor reflects the number of collisions that occur and is related to concentration. And the energy factor reflects the number of collisions that occur that have sufficient energy to overcome the electron cloud repulsion. And lastly, the orientation factor reflects the number of collisions that occur where colliding molecules are properly aligned. Okay, so not only do we need them properly aligned, which is what this showed, okay, we also need them to have more collisions because we need them to interact. They have to have enough kinetic energy to get close to each other, and they have to be orientated correctly. Okay, so that's all built into our constant, and this is all an effective temperature, or what I should say is that temperature affects all of these factors. Okay, so at the moment of collision, the reacting species are in the same state of high energy. The transition state is called an activated complex, and they have to overcome the energy barrier. So what exactly is that energy barrier? Well, the energy barrier is their activation energy, represented by capital E with a sub A. And this is the minimum energy needed to initiate a chemical reaction, energy needed to get over the energy hill, or in other words, the energy barrier. Okay, so here we have potential energy on our Y, and then the reaction progress on our X. And what we see is the path of the reaction. Okay, so we see it moving in this direction. So our products are reacting, or our reactants are reacting to give us our products. Okay, so as the reaction progresses, kinetic energy of the reactants is first converted into potential energy of the transition state. It is then transformed into kinetic energy in the form of the products. In other words, what's happening here is that we have to first build up enough energy to get into this transition state, so we have to have the energy to get there in the first place. But once we've built up enough energy to enter the transition state, now we can get over the energy barrier and proceed towards the products. So a good way of thinking of this is, I always like to use this ball on the hill analogy. So it takes us a lot of energy to roll this ball up the hill, but once it's here, it has enough potential energy to roll down on its own. Okay, then once we get over the hill, we can move all the way to our products, and that will be the complete reaction. And through this process, energy is of course conserved. So if the products have less energy than the reactants, some energy will be given off to the environment as an exothermic reaction. But it could also be an endothermic reaction. It doesn't necessarily reflect endothermic or exothermic. There's always some energy barrier that has to be overcome. Okay? And this hump, or the energy barrier, is called the activation energy. And so until you overcome that activation energy, the reaction can't proceed. Okay, so that's a factor of a lot of things, including temperature. We can put energy in the form of temperature. Okay, and I'm going to skip over the Maxwell-Boltzmann for now, and I want to jump to the Arrhenius equation, because I think this is important, and it's sort of where all of these ideas come into one place. So everything built into K. So our constant is made up of a lot of terms. So the activation energy, the gas constant, the temperature, and this all factors in the collisions that have sufficient energy for the reaction. Okay, so that whole term tells us how many collisions we have that actually have enough energy to complete the reaction. Okay, then we have P, which is the fraction of the collisions with the proper orientation. And last we have Z, which is the constant related to the collision frequency. Okay, so how many have the right orientation? How many how often are they colliding? And how many of them have enough energy? Okay, so this is all built into the Arrhenius equation, which is all built into K. So that rate constant is carrying a lot of weight. It's kind of the point I'm trying to make here. Constants, I think we always think of as being sort of, I don't know, like benign, kind of, like they're not really a big deal. We just kind of calculate them and who cares. But this shows you really how much effort went into figuring out this rate constants. Okay, we can kind of calculate them relatively easily. But if we want to know them accurately, look how much information is involved and how much stock that one little term holds. In other words, how much is really within that constant. There's a lot in there. Okay, and this is all wrapped up into the Arrhenius equation. And here we can combine a lot of terms, let them be represented by A, which is our frequency factor, which is a number that encompasses the fraction of collisions with proper orientation and the constant related to the collision factor, Z. So we can put P and Z all into one term of A. And we can manipulate the Arrhenius equation, and I'll spare you the details. Okay, but we can manipulate it until we get into the form of a line equation. So y is equal to mx plus b, where our slope of our line is EA over r. Okay, that's important. Our x values are 1 over t, and our y values are ln of k, while our b values are the natural log. Natural log of k is our y, natural log of a is our b. I think I said that wrong. Okay, but importantly, our slope value is EA over r, minus EA over r. Okay, so we can use this if we have some data. Okay, so we have some k values, we have some t values, we can calculate 1 over t, and we can calculate ln of k. We know r, that's a constant. Okay, so we can use this information to plot this data. So the 1 over t and the ln of k. And if we plot this, we come up with this. Okay, so we just have a line. So we have ln of k versus 1 over t. So what am I getting at here? What I'm getting at is the slope of this line is EA over, or minus EA over r. So if I'm looking to calculate the activation energy, I know what the slope of this line is. I know that's equal to minus EA over r. So all I have to do to solve for the activation energy, multiply by r. And notice in this case we use this form of r, the 8.31, where it's in kilojoules per mole over Kelvin. As we want it in terms of energy, because we're looking for activation energy. Okay, so we know that minus EA multiplied by, or the slope multiplied by r, gives us minus EA. Okay, so we can eliminate the negative sign here, because it's minus EA is equal to minus this. Okay, so our activation energy from this equation, or from this reaction, okay, which they don't even really mention what reaction this is, because it doesn't really matter. But the activation for the energy for this reaction is 186 kilojoules per mole. Okay, so this is all information. Let me go back for a second. This is all information you could determine from lab experiments. So you can determine what temperature it was conducted at. You can calculate K. We just showed how to do that by measuring reactant concentration and product concentration. Okay, then you can just convert those, and from that, you can calculate EA, the activation energy. Okay, so that's how you would practically use the Arrhenius equation. Okay, so hopefully that section was not as daunting as it may have looked if you looked ahead. In this next section, we'll talk a little bit about reaction mechanisms, and I'm going to kind of do the same thing where I'm not going to include absolutely everything that's in the chapter, but I want to try to get the point across pretty well. So what exactly is a reaction mechanism? So we discussed this briefly earlier, but it's just a sequence of reaction steps that describes the pathway from reactants to products. And these steps are called elementary reactions. And an elementary reaction is just a single step within a reaction mechanism. So one of the big things we think of when we think of kinetics, from like a synthetic chemist point of view, is generally speaking, we're going to use kinetics to try to show reaction mechanisms. Okay, so this is a very important thing, especially if you're a drug chemist and you're wanting to prove or try to explain how you've done a new transformation, like you're an organic drug chemist that's come up with a new transformation that makes it much easier to get from point A to point B for a very important transition. So maybe synthesizing a new molecule that's a good precursor for a drug or something like that. One way that they back up those studies is through reaction mechanisms, which means they run lots and lots of kinetic studies. Okay, so let's take a look at reaction mechanisms. So this is experimental evidence that suggests the reaction between, or let's just look at an example here. Experimental evidence suggests that the reaction between NO2 and CO takes place by a two-step mechanism. Okay, so this is our first elementary reaction. So we have NO2 plus NO2, and we have some rate constant, K1, gives us NO and NO3. Okay, so that's one single transformation. It's one single reaction. So it says at the bottom, the elementary reaction describes an individual molecular event. Okay, so we have a second reaction. Okay, so now we have NO3 plus CO gives us NO2 and CO2. And if we total those up, we get the overall reaction. So the overall reaction describes the reaction stoichiometry, and it is a summation of the elementary steps. Okay, so if I was to total these two steps, I would end up with my overall reaction. So meaning when we're actually, interested in what to put into the flask or what to put into our reaction mixture to actually make the reaction occur, we need this. Oh, where's my pen? There we go. Okay, so what we need to put into the actual reaction, or what's occurring in the reaction, is we have NO2 reacting with CO. Okay, and if we were to total these two, so here we see 1 NO2 will cancel with 1 NO2, and here NO3 will cancel with NO3. And we know that NO2 is one of our reactants, so we would just refer to this as a reactant. But one special piece of this would be the NO3. And this would be a reaction intermediate. And it's a reaction intermediate because it's formed by one elementary step and then consumed by another elementary step. So it won't be present in the overall reaction. So it would be canceled out, in other words, when we actually total these up. So that's an intermediate. So if I was to present to you a couple reaction steps like this, you should be able to pick out a reaction intermediate. And a couple terms here. So molecularity is a number of entities, or in other words, molecules or atoms that participate as reactants in an elementary reaction. So we have unimolecular, bimolecular, and termolecular. So uni, just 1, bimolecular 2, and ter 3. Okay, so if we have something like ozone decomposing to oxygen and elemental oxygen, okay, that's unimolecular. If we have ozone reacting with atomic oxygen to give us O2, that's bimolecular. And if we have 3 things, then it's termolecular. Okay, so this last one, maybe we have a metal catalyst driving the reaction. Okay, so simple as that. So if you have 1 thing, it's uni, 2, bi, 3 term. And I'm only referring to this, my reactants, not actually the products. Okay. And of course, depending on how many species we have reacting, our rate laws are going to look somewhat different. So if we just have A going to products, we would look like a first order. If we have in other words, A twice, so 2A, we'll end up with a rate something like K times A squared. Okay, and you can go on down the list. So it says for an overall multi-step reaction, it is not possible to derive the rate law from the stoichiometry of the chemical equation. It must be derived experimentally. But at the top it says the rate law for an elementary reaction can be derived directly from its molecularity, because the elementary reaction is an individual molecular event. So I can use the stoichiometry to determine my rate, so my rate orders for individual elementary reactions, but I can't use it for an overall reaction. So what I was telling you before was not untrue. It's just when we're dealing with elementary reactions, we can use it this way. So just as an example, do I really want to do this one? Let's look at this one. Okay, so it says the following 2-step mechanism has been proposed for the gas phase decomposition of nitrous oxide. Okay, so looks like this. So we have N2O goes to N2 and O. N2O plus O gives us N2 and O2. Okay, so it wants to write the chemical equation for the overall reaction. So in other words, it wants us to total these. Okay, so to do this, we can cancel out anything on both sides. So O cancels with O. N2 can't be canceled. N2O can't be canceled. Okay, so we ended up with just adding these together. So cancel those out, total them up. And you end up with 2N2O, since it appears twice, gives us 2N2, again, since it appears twice, and then we get O2 at the end. So that's our reaction. So it wants us to identify any reaction intermediates, so something that's generated by a reaction but then is consumed. So just elemental oxygen there, O. Okay, that's the only one. And it wants to know what's the molecularity of each step. Okay, so it wants us to say whether it's uni, bi, tri, or ter. So the first one, we just have a single decomposition, so that's unimolecular. Second one, we have two things reacting, so that would be bimolecular. Then lastly, it wants to know the overall reaction. Okay, so the overall reaction, we have two things reacting. Okay, so N2O reacting with N2O, so that would be bimolecular. Okay, so hopefully that was not too tough, just learning to total up elementary equations and look for intermediates and then be able to spot the molecularity of each step. Okay, so here we'll talk about the rate determining step. And I mentioned this a little bit earlier. So it's like sort of the idea of sand moving through this sort of glass system we have here. Okay, so at first we just think about the sand. Oops, sorry about that. Okay, so just the sand moving through the glass. So we see that we have a narrow opening and then two wide openings. So what will control the speed of the sand as it falls down through the glass? So even if we had a wide opening here, but then a narrow opening here, it would still be that the narrow opening controls how fast the sand can move from the top to the bottom. No matter what configuration they're in, that narrow opening will always limit the fall of the sand. Okay, so this is like having a reaction mechanism. Okay, let me go back. Oh, my computer's getting angry with me. Okay, so we have reactants, and then intermediate 1, intermediate 2, it's a product. And if this first step is slow, or if any of the steps are slow, that would be the rate determining step. In this case, it's our first reactant step. That's the rate determining step. Okay, so what do we mean by this? So rate determining or rate limiting step. So it's the slowest step in a reaction mechanism, and it acts as a bottleneck and limits the rate at which the reactants can be converted into products. And the overall rate law can always be determined from the rate determining step. So it says the rate law for the overall reaction can be derived directly from the stoichiometry of the rate determining step. The overall rate law comes from the rate determining step. So if we take a look at this, so we have NO2 plus NO2 gives us NO and NO3, and then we have a second step, and then we have an overall reaction. And they go ahead and they mention here that this is a slow step. Okay, and we know that the rate will always be limited by the slow step. Okay, so based on this information, our rate would be equal to our constant times NO2 squared. Because remember, from elementary steps, we can determine our reaction order based on the reaction stoichiometry. Okay, so we can actually figure out the rate law just based on these elementary steps. Okay, so with this problem, it says the following overall reaction has been determined experimentally to have a second order rate law. And they give us the reaction NO2 combines with fluorine to give us NO2F. And they give us a rate law. And they give us two steps. And what they want us to do is they want us to prove this rate law based on these steps. Okay, so the first thing we need to do, let's write a rate law for each of these. So remember, we're only focused on the reactants. So the rate law for the first reaction would just be K times NO2 times F2. And they both have 1-to-1 stoichiometry. Okay, so our superscripts are both 1. For the second reaction, we have NO2 plus F gives us NO2F, so our rate law is just K times NO2 to the first times F to the first. Okay. And so we can see that if we total these, okay, fluorine by itself would be reaction intermediate. And if we're to total these up, we end up with 2NO2 plus F2 gives us 2NO2F, which would have a different rate law than what we were given. But if we know that one of these must be the rate determining step, and we see that the rate here is equal to the rate we're looking for, that must be the slow step. Okay, so it's kind of a way to verify. This is kind of an odd question, not necessarily one I would give you. Mostly what I was interested here is just to show you how you can devise these rate laws from the individual steps themselves. So without me telling you one of these is the slow step, it would be kind of difficult for you to know which one to pull the rate law from. Okay, but if you do know which one is the slow step, then you could do the same process and know how to pull the rate, or where to get the rate law from. And kind of moving back to this for just a moment, if we know we have an intermediate, that might be one way of knowing that the first step is the slow step. Not necessarily. Okay, but let's move on to the next one. Okay, so here they've told us which one is the slow step. Okay, so here we have NO2 reacting with hydrogen to give us N2O, N2, and H2O. Okay, so if we wanted to determine the rate law for this overall reaction, we would find the slow step and write the rate law based on that. Okay, so the rate law would be K times N2O2 times H2. Okay, and what's interesting here is it actually contains an intermediate. And I think I'm going to kind of gloss over this part a little bit. Let me see. Okay, this problem I just want to go over with you just to kind of show you how you could derive a rate equation through substitution. So here it says gaseous hydrogen and iodine combine to produce gaseous hydrogen iodide, and it says it's an overall second order reaction. So if we were just trying to write a reaction, a rate law based on the slow step, we might write this. We might write rate is equal to K, we'll say K2 because that's what it tells us, times I squared plus, or sorry, not plus, times H2. But it tells us it's a second order reaction. So 2 plus 1 is 3, so this can't possibly be the rate. Okay, so if we study this reaction, we realize it's second order. And if we just try to derive the rate from our slow step, that won't work. So what we can do is we can derive this through substitution. So our initial rate we would write would be the rate is equal to the constant times I squared times H2. Okay, so we're including a reaction intermediate. So what we can do is through substitution, okay, so we're including a reaction intermediate, and again there, we're just basing this based on the stoichiometric coefficient since it's an elementary step. Okay, so instead, let's look at our reversible reaction. Okay, so this top reaction. So this is an equilibrium reaction, so we can write a forward or reverse reaction. So we can write that the rate is equal to K1, so K1 is the forward reaction, times the reactants for the forward reaction, which is I2, and that's going to be equal to the reverse rate. So K minus 1 times I squared. So what we can do now is we can sub this in. Okay, so the next step. So rearrange the solve for I squared. So we can say that I squared is equal to K1 over K minus 1 times I2. Now, if we plug that in instead for I squared, look what we end up with. So we equal rate is equal to K times K1 over K minus 1 times I2 times H2. We can simplify our K terms all into one constant. We end up with the rate law. Rate is equal to K times I2 times H2. Okay, and that's the overall second order, and it matches with what they suggested. Okay, so it's a plausible rate law for this. Okay, and that's probably a little beyond with what I would necessarily expect. I would be more interested in you being able to write a rate law from the slow step. Okay, here's another example if you want to take a look at it. Okay, so in this last section we will talk about catalysts. And what exactly is a catalyst? So a catalyst is a substance that increases the rate of a reaction without itself being consumed by the reaction. And a catalyst may be used in one step, but will be regenerated in a later step. So the simple way of looking at a catalyst is just to say it speeds up a reaction. But in many cases, a catalyst will actually unlock a path for a reaction that wasn't previously accessible in any way. So it can actually create a new pathway. So it can actually facilitate a reaction in such a way that you can do a reaction that wasn't previously possible without the catalyst. But in many ways, it's used to essentially make a reaction more efficient. Okay, that's one way of looking at it. Another way of looking at it is that many times it's needed to actually complete the reaction to begin with. So no matter how fast or slow the reaction is, now it's possible. Or it could just be, again, that it opens up a different doorway to a reaction path that's faster and more efficient. And especially if you're, say, in chemical industry, trying to produce ton quantities of something, if there's a catalyst that can make your life easier or make your process more efficient, of course you're going to want to use it. And many times, this might be a metal catalyst that they can recover at the end. That would be termed like a recoverable catalyst, where maybe we can filter it out, or maybe we can use a magnet and filter it out that way. There's also a sacrificial catalyst that's actually consumed. Okay, but for our definition, we're going to say that it's used in one step of the reaction and regenerated at the end. Okay, so just as an example, so it says the rate of the decomposition of hydrogen peroxide can be monitored qualitatively by collecting the involved oxygen in a gas balloon. And so here we have a setup where we're looking at the decomposition of aqueous hydrogen peroxide. So we have water and we have hydrogen peroxide, and they're added to each other. Now, without the presence of the catalyst, you'll see that we get very little oxygen trapped in the balloon. If instead we add a catalyst, okay, so after addition of aqueous sodium iodide, the balloon rapidly inflates with oxygen. Okay, so this is lowering the activation energy, it's maybe creating a new pathway, and it's increasing the rate of the reaction. Okay, so how can we spot them if we have a reaction mechanism written out with equations? So what you'll see, and this is for this actual reaction, so hydrogen peroxide being combined with I- iodide to give us oxygen, water, and of course regenerating iodide itself. So how will you know something is a catalyst? Well, one way you'll know is that it's added to one step, so it's in the initial reaction mixture, or it could be added later. Okay, and it's also regenerated, so it wasn't consumed in any way by the reaction. So this is generated by the reaction and then consumed. That's an intermediate. But if something is initially consumed and then regenerated, that's a catalyst. And notice it still gets canceled out. So in our overall reaction, we still just have hydrogen peroxide gives us water and oxygen. Okay, but this reaction was facilitated by a catalyst, and you know that because you put something in that you also got back out. Okay, and it's not mentioned in the overall reaction. Okay, so it says since the catalyst is involved in the rate determining step, it often appears in the rate law. Okay, so if it is in the rate determining step, yeah, you might write it into the rate law. So here we have sort of what I was talking about in terms of energy. So we have the catalyzed pathway versus the uncatalyzed pathway. Okay, so with this mechanism, the first step was the rate determining step. So we see here that it has a higher activation energy. Okay, and then the uncatalyzed reaction, we just have one large activation energy. So notice that not only is the activation energy of the catalyzed pathway lower, but now we have two steps. So here we just have one step. So not only does it lower the activation energy, it actually creates a new pathway. Okay, so that's kind of the point I'm trying to stress here. So it lowers the activation energy, speeds the reaction, and it does that by opening a different pathway that wasn't there before. So it says, note the presence of the catalyst does not affect the energy difference between the reactants and the products. No. So our reactants and products are still the same energy level. So if it was exothermic, it's still going to be exothermic. If it's endothermic, it would still be endothermic. Okay, so it's just affecting that pathway. And there's two types, so homogeneous catalyst and a heterogeneous catalyst. So homogeneous means that it's in the same phase. So if everything's in the solution phase, then it's in the solution phase. If everything's in the solid phase, then it's in the solid phase. A heterogeneous catalyst would be in a different phase. So maybe we have a solution mixture where our catalyst is maybe as a solid. Maybe it's embedded on carbon that will keep it suspended, something like that. Okay. Heterogeneous catalysts are very popular in industry because they can be removed very easily. So I can reuse them for several cycles, maybe thousands of cycles, I don't know. Okay. So some examples of catalysts you'll know are in your catalytic converter. Okay, so this takes the gases that come out of our engines that we don't want to put into the atmosphere, CO, NO, and O2. Okay, it actually converts them to gases that are supposed to be, more pleasant for the environment. And so this comes out your tailpipe, now a CO2 water into an O2. So that's a lot better than putting unreacted alkyl species, CO and NO. We don't want to put those into our environment. So this converts it to something a lot nicer. This is an example of a heterogeneous catalyst. So everything that it's reacting with is in the gas phase, but it itself is in the solid phase. So it's heterogeneous. A homogeneous, so here we see H2O2. So in the absence of a catalyst, it decomposes very slowly. But if we add something like sodium bromide as a catalyst, okay, then it reacts. So the buildup of Br2 leads to the rapid evolution of O2. Okay, so it's actually acting as a catalyst. Okay, then after all of the H2O2 has decomposed, a colorless solution of sodium bromide remains. Okay, so it's catalyzed the reaction. What they're trying to say is it's catalyzed the reaction, but it wasn't consumed by it. So this would be a homogeneous catalyst. That's the only point I'm really trying to make, is that it's in the same phase. Another kind of catalyst is an enzyme, and these generally are biological in nature, so it's a homogeneous biological catalyst. Okay, so here we see sucrose. So here we see sucrose being broken down into glucose and fructose. Okay, and the enzyme is the part doing the catalysis, and the substrate is the part actually where the work is being done. So sometimes these are good to picture as this type of system where we have the enzyme, and when you get more into biochem, you'll study this a lot more, where we have the substrate, which is the thing being worked on, the enzyme, the thing doing the work. So it comes in, it can bind, and they refer to this often as a lock and key mechanism where only certain substrates can fit certain enzymes. Okay, so they come in, some reaction occurs here, bonds are broken, and then they both leave as the products. Okay, so that's just the very extreme basics of how an enzyme works. Okay, so this is kind of a zoom in of that. I'm not going to get too far into this, but you can kind of see how it strains the bond to be inside of this enzyme, and eventually that bond is weak enough that it can be broken. Okay, so that will wrap it up for this chapter. I know this was a long one. Well, this one wasn't that bad, but